I'm going to talk about an interesting problem, variant of the vehicle routing problem. The classical vehicle routing problem is a generalization of this traveling salesman problem, which is known to be NP-complete. But I'll introduce a new variant called the fixed time vehicle routing problem. Essentially, this variant is can be reduced to the min cost bipartite matching problem, which is polynomial time solvable. So in that sense, this problem is not NP complete. It's solvable in polynomial time. If you take the Euclidean version of this problem, then one can reduce it to Euclidean min cost matchings, for which there are solvers. So you can essentially use one of the existing solvers to compute the optimal solution. The thing though is that existing solvers for Euclidean bipartite matching take quadratic time. Nothing better is known for Euclidean bipartite matching. So if we, but the instances of Euclidean bipartite matching that we get from this reduction have special structure. So what we're going to do is we're going to exploit that special structure and actually design an algorithm that runs into the 1.8 time and computes optimal solution for fixed time vehicle routing problem. Okay, so that's the general overview of my talk for today. Okay, let me begin by introducing the problem. Imagine, so this is what I refer to as the fixed time vehicle routing problem. So you're given k servers. You can think of these as vehicles, for instance, and their initial locations. So S1 through Sk are the locations of the k servers. So in this example, for instance, the squares represent the initial locations of the servers. And then you're given a sequence of requests, R1, R2, all the way through Rn, where here the index, so these requests are given by their location, but they're also given by their, they're also given, along with them, you're also getting the time at which they are supposed to be serviced. For instance, here the index of the request will denote the time at which this request has to be serviced. Okay, and the goal for us is to actually design a path for each of the servers, and the property of these paths should be the following: that you should, if you walk along this path, the index of the request should keep increasing. In other words, you should process these requests in chronological order. Okay. Just to make this more concrete, you can think of school buses. So you have, let's say S1, S2, S3 are 3 school buses and their initial current locations. And let's say the 10 request locations that are given are the locations from which you have to pick up kids. And with each one of them, there is a pickup time associated. So you have to have the bus be there at that time, right? So if you design a path for each bus, you'll notice that the path will visit these locations in increasing chronological order. So it will go to R4 first, R8, and R10. Cannot go to R10 before R4, for instance, right? Because the time at which R10 has to be serviced is later, after R4. Yeah. So the goal is, given this constraint on the path, the goal is to compute the set of k paths that minimizes the total Euclidean distances of all the edges on these paths. Okay. If there are questions, please feel free to ask questions or clarifications on the problem. So I'm going to assume that basically you can move from any request location to the next one instantaneously. In other words, these vehicles are moving with infinite velocity. One can relax that condition and the algorithms will extend to those settings. However, I want to keep things simple, so I'm just going to assume that requests can be processed, like basically these vehicles move at infinite velocity. Okay. This is in graph theory, this is also called the k-Disjoint path cover problem in a directed acyclic graph. So you can always sort of also visualize this problem as follows. You basically imagine a directed graph. Essentially, you have edges between every pair of requests, but there are directions associated with these edges. So basically, you have an edge going from lower indexed request to a higher indexed request. So the directions are from a lower indexed request to the higher indexed request. If you construct a graph like this, it will be a DAG, because you'll never sort of create a cycle, you'll never come back in time using a directed edge. So the problem now, if you consider this DAG, the problem is now to compute a minimum cost k-disjoint path cover in this DAG. So basically a set of k-disjoint paths that cover all the requests. Okay, so I'm going to describe the reduction to matching. So basically, I'll show now that this problem reduces to computing minimum cost bipartite matching. So what I'll do is I'll take, remember that the input to the fixed time vehicle routing problem is the set of k initial locations and a set of end requests. So I'm going to create a bipartite graph using this input. The way I do that is as follows. What I'll do is for each initial location of the server, I'm going to create an exit node. So there are k initial locations, so I create k exit nodes. And for each request, I'm going to create an entry node and an exit node. Okay, and these nodes will be, in terms of their location, they'll be co-located. So they'll be at the same location. Okay. So this way I've created n plus k exit nodes, one for each initial location and one for each request, and n entry nodes. Okay, so this will be the bipartition of my graph, right? The entry nodes is one side, exit nodes is the other side. Now what I do is I'm going to create edges from each exit node, either of a request or a server, to another entry node of a later request. So I'm only going to add edges from exit nodes of earlier requests to entry nodes of future requests, because that's kind of that's sort of modeling the constraint that you have to visit requests in increasing chronological order, right? And I assign the weight of each edge to be Euclidean. All right. So if I do this, this will give me a bipartite graph. It's not a complete bipartite graph, but because only exit nodes are only connected to entry nodes of the future requests. But basically, if I take this bipartite graph and compute a minimum cost matching of size n in this graph, that would correspond to the optimal solution for the fixed time vehicle routing problem. It's actually a pretty, if you think about it a little bit, it becomes obvious as to why this is the case. Essentially, what you have to do is you have to look at, remember this graph has n plus k entry nodes and n exit nodes, and we're computing a matching of size n. So there are at least there's exactly k exit nodes that are unmatched. So you can basically take those exit nodes that are unmatched. They would either correspond to a request or to an initial server location, because the exit nodes only come from these. So if it's a request, then you can treat this as the last vertex on the path and then sort of backtrack to compute the entire path, right? So basically what you have to do is you have to look at the entry node of the corresponding request whose exit node is unmatched, and then look at its match. It'll be an exit node of a prior request, some prior request. So you can sort of do this, and because every entry node is matched, you'll sort of backtrack, and the only time you stop is when you encounter initial configuration. So this way you can trace out a path for each of the unmatched exit nodes, right? Also, you can argue that there cannot be a cycle in this simply because of the way we created the graph. It just only go from exit nodes of lower index to an entry node of higher index. So you can argue that this will not create cycles. So basically all requests fall on one of these k paths. Okay, so this is the reduction. So all we have to now do is compute min cost matching. To solve this problem, we have to compute min cost matching of size n in this bipartite graph. Please let me know if you have any questions. Okay, so I'm not sure if how many of you are familiar with the online algorithms community, but this problem fixed time vehicle routing problem can be seen as basically the offline analog of the classical k-server problem. K-server problem is a problem central to online algorithms. So it's an online problem. Essentially, you have these requests coming in one at a time, and you have to make decisions on which server is going to serve this request without the knowledge of future requests. Basically, we are looking at the entire sequence being given in advance, and now you have to find the best offline solution for this problem. So that's what that's how you should view. I mean, the one way to view fixed time vehicle routing problem is it's simply the offline analog of the classic k-server problem. So in 1990, and I believe this was the first SODA, Chirobak et al. Basically gave a reduction of the offline k-server problem to min cost flow with lower bound. So this was, so in that sense, it was known that this problem is polynomial time solvable since 1990. But this problem is a little bit more complicated. Min cost flow problem with lower bounds is a little more complicated than, say, bipartite matching. So our reduction is to much simpler min cost bipartite matching. Right. Just to give you an idea, so independently, of course, geometric bipartite matching has been studied extensively for the last several decades. The problem is essentially the following, that you're given two sets of points, let's say in two-dimensional space, the red set and the blue set, and you're given a complete bipartite graph on this set of points. And the goal is to compute a set of vertex-disjoint edges of cardinality n, which has the smallest possible cost, right? So for instance, in this example, you're matching the red and blue points, and this is not the minimum cost matching. You can do better by simply connecting these 2 points here, these 2 points here, and these 2 points here, instead of the 3 matching edges that we have here, right? So you can actually get a cheaper matching in this example. But the goal of geometric bipartite matching problem is to compute the matching of the smallest total cost. And it turns out that the matching instances that we are generating for fixed time vehicle routing problem can be solved using some of the algorithms that have been developed for geometric bipartite matching. So what I'll do is I'll basically give you a summary of what's known. So if you are given real valued costs, you can basically graphs with real valued costs, bipartite graphs with real valued costs. Then you can run this classical Hungarian algorithm, which runs in n-cube time, to compute the minimum cost bipartite matching. I'll give an overview of this algorithm, basically a geometric visualization of this algorithm very soon. But essentially, if you're dealing with geometric data, you can, there was this very nice paper by Vaidya in, I think, 1989, where he showed that if you're dealing with Euclidean costs or L1 distances, then you can basically develop geometric data structure that can speed up Hungarian algorithm and improve the running time from n-cube to n-squared, right? And that's been the state of the art since. So we do not know how to improve upon this quadratic complexity. It's been several decades now, but we haven't been able to make substantial progress. There have been some special cases where one can do better. For instance, I had a paper in 2030 in SOCG where we assumed the coordinates were integers, and we're dealing with Euclidean distances, so the costs were square root of integers, so they're real valued. And that too in two-dimensional space, and we were able to get the running time down to into the 3/2 log gamma, where gamma is the bound on the integer coordinate, right? But it's and this result did not extend to higher dimensions. So getting quadrats or sub-quadratic algorithms generally for Euclidean bipartite matching, or generally for LP distances, is a major open question in computational geometry, right? So one of the things that when we came up with this reduction for vehicle routing problem, fixed time vehicle routing problem, one of the things we started looking at was whether the matching instances that are being generated by fixed time vehicle routing problem are easier to solve. Can we design sub-quadratic algorithms for these problems? That's kind of the goal that we set out with. So it turns out, though, we were able to argue that fixed time vehicle routing problem is as hard as geometric bipartite matching. In other words, if you can actually solve fixed time vehicle routing problem in sub-quadratic time, you can design a sub-quadratic algorithm for geometric bipartite matching. And it's a very nice and simple reduction. I want to sort of explain to you what that reduction is. So imagine you're given in 2 dimensions, within a unit square, you're given an instance of Euclidean bipartite matching, or geometric bipartite matching with L1 costs, not Euclidean, but L1 costs, right? So you have 2 sets of points, red and blue, that are inside the unit square. What I'll do is I'll create a 3-dimensional instance of fixed time vehicle routing problem for this using these points. And the way I do that is as follows. I will designate all the red points as the start location of the n different servers. Okay, so we have n servers now. So I've set the value of k to be n. And so these red points become the start initial configuration of the n servers. And what I'll do is now I'll arbitrarily order the blue points, the B points of B. Let's say B1, which is the first point, will become the first request. And what I'll do is I'll lift it to the 3rd dimension and assign a coordinate value of 3 to the n. The z coordinate value is 3 to the n. Okay. The second point of B will be lifted, but the coordinate value becomes 3 to the n minus 1. Right? And the third point will be 3 to the n minus 2 and so on. Right? So I'll create this 3-dimensional instance. So B1 is my first request, B2 is my second request, B3 is the third request, and so on. So now what happens is, some server has to process the first request. So whichever server processes the first request has no incentive to move to the second request and serve that too. The reason is the distance between the first request and the second request is 2 times 3 to the n minus 1, right? Whereas all these servers that are in the start configuration, they are at a distance of 3 to the n minus 1. So they're closer. The servers, the initial configurations are closer than the distance to the first request. So the server that serves the first request will not serve the second one. In fact, it will be a different server. And you can continue this argument and show that every request is served by a different server, right? So in the end, what happens is you get n distinct paths. Each path is essentially a single edge, and what you end up getting is a matching. And because we are dealing with L1 distances, the costs are sort of decomposable. In other words, you can argue that the matching that you get here as the optimal solution for the fixed time vehicle routing problem is also the optimal solution in the 2-dimensional plane. The reason is you can argue that every matching between red and blue points prior to lifting, if you take that matching and now you look at its cost in the lifted space, in the 3-dimensional space, then the cost is shifted exactly by 3 to the n plus 3 to the n minus 1 plus 3 to the n minus 2 all the way to 3, right? So each matching cost, no matter what matching you take between red and blue points, their matching cost is shifted by the same amount. So whatever was minimum cost in the 2-dimensional unit square will also be the minimum cost in the 3-dimensional set, right? So in other words, if you take a fixed time vehicle routing problem solver and you use that to compute an optimal solution, then you can use that, whatever optimal solution is, will also correspond to the minimum cost matching under L1 cost for the original instance. Okay, so in some sense it's disappointing because basically what I'm saying is, hey, fixed time vehicle routing problem instances are as hard as the general version of the Euclidean or L1 bipartite matching. So so is there anything interesting we can do now, right? Then it turns out that if you observe here, the instances that we had to create, we had to set coordinate values to be extremely high, right? The third coordinate was 3 to the n. So if you look at the spread of the instance we have created, that's exponential in n. So natural question to ask, therefore, is if we assume that the spread is bounded by a polynomial in n, can we do anything better? And that's kind of the focus of what I'm going to present next. So I'll present an algorithm that runs in n to the 1.8 log delta time, where delta is the spread of the points. Right? So spread is simply the ratio of the diameter to the closest pair of points in the input. Okay. All right. So what I'll do is I'll quickly give you a geometric visualization of Hungarian algorithm, and then I tell. Then I'm going to present the algorithm for the fixed time vehicle routing problem. Hungarian algorithm is this classic graph algorithm that helps us compute the minimum cost matching. There are two definitions that's worth knowing that will help you understand Hungarian algorithm better. The first one is augmenting path. Most of us see this as part of grad or undergrad algorithm classes. Essentially, if you have a matching between red and blue points in this example, and augmenting path is simply a path that starts and ends at a free vertex being a vertex that's not matched yet. And then if you walk along this path, you'll see that you alternate between edges that are not in the matching and edges that are in the matching. So the solid edges are currently in the matching, the dashed edges are not in the matching, right? So this would be an augmenting path. And if you and the process of augmenting along this path is simply involves removing the matching edges that are on this path from the matching and adding the non-matching edges or edges that are not in the matching to the matching. So in other words, you'll delete these two edges from the matching and add these three edges to the matching. And if you do this, you increase the size of the matching by 1, right? So typical matching algorithms start with an empty matching and then iteratively keep computing an augmenting path, augment the matching along this path, and end up sort of stopping when they cannot find any more augmenting paths. So that's how max cardinality matching algorithms work. If you want minimum cost matching, so typically the way it works is you maintain a set of non-negative weights on the points and maintain a matching that we call feasible. So matching is and a set of dual weights are feasible if these conditions are satisfied. So I'm going to also go through these conditions, but also give a geometric visualization of these conditions. Okay. So the property of the weights that we assign should be the following. For every edge in the graph, the difference in the weight of B and A. So B is a point from the set B, capital B, and A is a point from the set capital A. So if you take any such edge, the difference in the weight of B and A should not exceed the Euclidean distance or the distance between B and A, right? So this is the property we should have. And for matching edges, we should have this property hold with equality, right? So the difference in YB minus YA should be equal to the distance between A and B. So it's well known from linear programming duality, you can argue that a feasible perfect matching being where every point is matched, a feasible perfect matching is a minimum cost matching. And our goal, therefore, when it typically most of the algorithms that work in this space, their goal is to find a feasible perfect matching. In other words, find a perfect matching that satisfies these conditions. A useful definition is that of slacks. So slack is simply the gap. If you look at this equation here, the first one, it's the gap in the RHS and LHS. So what is the difference of the RHS, that is the distance between A and B, and the difference in the weights, like that value is the slack. And because if you take any feasible matching, the slacks will be non-negative. Okay, now let's understand these constraints from a geometric viewpoint, right? So think of, so I want you to interpret the weights as follows. Think of the weight of B, YB, as being the radius of a ball centered at B, right? So I want you to think of YB as a disk, the radius of this disk, blue disk, right? And similarly, YA is the radius of this red disk. These weights are always guaranteed to be non-negative, so you can always define some sort of a disk in this case, right? And so the constraints that we are looking at, every edge will have to satisfy this constraint, the third one, which is YB minus YA is less than or equal to the cost of the edge. So visually that means that the red disk can either be touching the blue disk from the inside, or it can be protruding out of the blue disk. These are the only two possibilities. You cannot have this first case happen. You cannot have the red disk be completely inside the blue disk. If that happens, then you can argue that YB minus YA will be equal to greater than or equal to, I should say greater than A minus B, which makes it infeasible. So in some sense, these weights are maintained in such a way that you have either condition 2 or 3 happen, not 1. So that's kind of how the algorithm, the Hungarian algorithm works. It starts with an empty matching. It sets all the dual weights to be 0. So essentially our disks are of 0 radius. And now it starts to adjust these weights. In other words, it starts to grow the disks and tries to maintain feasibility and tries to find a path consisting of 0 slack edges, augmenting path consisting of 0 slack edges, and augments the matching along this path. So when you do that, what happens is, because all the edges are 0 slack, the newly entering matching edges now also continue to satisfy the second condition that is needed, right? So let me show you an example where this is how Hungarian algorithm typically works. Basically all the free points are continuously growing their disks and trying to find matching edges, like basically augmenting paths. So I'll show you a non-trivial case. Hopefully I can stop it at the right place. Right. So if you look at this situation now, you see this free blue point, and it's forming an admissible or 0 slack edge with this red point, meaning the red disk is touching the blue disk from the inside. So it's actually 0 slack. And this matching edge again is forming a 0 slack edge, is a 0 slack edge. And similarly, this edge is also 0 slack. So now if you augment the matching along this augmenting path that starts at this blue point and ends at this red point, then you'll be guaranteed to maintain feasibility. So you can continue doing this. And all these algorithms do is exactly this. So right now what you saw here is that you have an augmenting path again of admissible edges. So you can augment along this path without violating feasibility. This is exactly how these algorithms work. At least the Hungarian algorithm works. So the adjustment of dual weights, essentially what happens is this adjustment of dual weights can be basically reduced to running Dijkstra's on a graph, basically Dijkstra's shortest path algorithm on a graph where edge weights are replaced with slacks. And so you can, if you're dealing with an arbitrary graph, you can basically execute Dijkstra's in order of n squared time. The total, and once you adjust the dual weights, you find an augmenting path. So you're increasing the matching size by 1. The number of iterations this runs is at most n, because you're trying to look for a perfect matching. And so the total time taken by these algorithms turn out to be about n cubed, right? So in 2 dimension, one can speed up Dijkstra's execution by using dynamic bichromatic closest pair data structure. This is essentially a variant of the weighted Voronoi diagrams. And you can get an improvement in execution time from order n squared to order n. Basically, there's some hidden log factors here. But what that means is that you end up getting an execution time of n squared. Right? So this is the source of improvement in geometric setting. Basically, the dual adjustments can be done faster if you're dealing with geometric data. For vehicle routing problem, the version that I described, you can get a slightly better bound of nk. But as you can see, using the same techniques, but as you can see, when k is theta of n, this is still quadratic, right? And both from a theory standpoint as well as from a practical standpoint, the interesting case is when k is theta of n. Like if you look at the reduction that I gave you, the reduction from vehicle routing problem to matching, I had to set k equal to n, right? And similarly, if you're really looking at real world scenarios, most times as you scale the number of requests, you have to also add more resources to serve those requests, because typically like something like a taxi or a school bus in a given day can only serve so many requests. So you'll see that the number of servers required scale linearly with the number of requests. So from both standpoints, this result is not exactly that exciting, the improvement to NK. Okay. All right, so what I'll do now is I'm going to present the algorithm for fixed time vehicle routing problem. It's actually a nice and simple algorithm. But instead of presenting it for fixed time vehicle routing problem, I'll present it for a different, I'll present this algorithm for stochastic data. Okay, and I'll tell you what that means. Essentially, it's easier to describe the algorithm in this stochastic setting. But once I describe for this, but this algorithm that I'm going to describe, that also extends to fixed time vehicle routing. Okay, you can use it even for that fixed time vehicle routing problem. It's the same algorithm. Okay, so what is stochastic data? Right? What is this problem? So imagine I have a unit square and I draw two sets of points from the same distribution. So the unit square, so the distribution is defined over the unit square, and I'm taking two set of points A and B that are samples from this distribution that are drawn independently, and both there are n samples. The first set of A is the set of endpoints that were sampled from this distribution. B is another set of endpoints sampled from this distribution. And my goal is to compute the minimum cost matching between these two sample points. Right? So that's the stochastic version of the geometric bipartite matching problem. So for this, I'm going to give you a very simple n to the 1.75 log delta time algorithm. And I'm going to show that the same algorithm also works for fixed time vehicle routing. And the only difference is the execution time is going to be n to the 1.8 log delta for fixed time vehicle routing. Okay, so let's try and understand what the intuition is for designing algorithm for stochastic. Right? If you're drawing points from the same distribution in a unit square, then one can argue the cost of the optimal matching grows at the rate of square root. So what does this mean? Essentially, you have n. If you take n samples and compute the cost of the matching, you can upper bound the cost of the matching by about square root of n log n. So in other words, if you take the average cost of an edge in the matching, it sort of grows, it is 1 over square root of n. So in other words, as n increases, the average cost of the edge in the minimum cost matching is become smaller and smaller. And that's not surprising, right? You're drawing points from the same distribution. So every red point should have a close by blue point. It can match to. You don't have to have long edges in the matching. Right? So this sort of figure hopefully shows you that, if you try to match blue points to red points, most of them will basically match locally. Doesn't have to work. You don't have to have a long edge connecting them. All right. So natural question therefore is, how about we use a divide and conquer strategy and execute the Hungarian algorithm that we saw in this divide and conquer framework. So the idea is I break my problem into 4 subproblems and run this Hungarian algorithm recursively on these 4 subproblems, right? And find some sort of a matching in each of these 4 subproblems. The idea is that most of these optimal edges will perhaps be discovered in smaller subproblems, and the amount of work you do to merge them is going to be small, right? And so if we can show that the amount of work done to merge is sub-quadratic, then we'll get an overall execution time that is sub-quadratic. We could do that, except we'll run into trouble if we do it in a naive way. So if I, for instance, take my subproblem and divide it in, rather take my problem and divide it into 2 subproblems like shown here, and recursively compute a feasible matching here and a feasible matching here. This is good. Every edge inside that is completely inside one of these subproblems will be feasible, but the weights that I assign to these points may not, like if you look at edges that cross the boundary, those edges may not satisfy the feasibility conditions. For instance, you may have a situation where the point, the blue point here, if you look at the weight assigned to this, the point B, its dual weight is if you look at the subproblem to the left, the dual weight is feasible. But if you look at the edge B to A prime, if the disk of A prime is completely inside the disk of B, which means this is basically infeasible, right? So you cannot now merge easily because the dual weights are not compatible. So in order to overcome this problem, we came up with a very simple trick. We basically said, how about we restrict the dual weight of every point to not go outside the subproblem. Right? Basically, for instance, if you look at the figure on the right, the dual weight of B is restricted to be inside the subproblem, and therefore the disk stays completely inside the subproblem. So if we do this, we are guaranteed that no edge that is crossing the boundary will become infeasible, and so it becomes very easy to combine solutions. This is the dual view. If you take the primal view, the way to think about this is, imagine that every point of B can either match to a point of A or match to the boundary. If it had this additional option of matching not just to points of A, but also to the boundary of the subproblem, then that would be the primal interpretation of what I just described, right? Basically, so that's the recursive subproblem that we're trying to solve. We are trying to find a minimum cost matching where every point of B either matches to a point of A or matches to the boundary. Okay, so that's kind of what we are recursively solving in each of these subproblems. And so in terms of actual feasibility condition, now we have to, in addition to the original feasibility condition, we have to add two more feasibility conditions. The first one is that we don't let the dual weight of any point of B go outside the subproblem. So this notation here, D of B comma cell, is simply saying it's measured, this value is the distance of the point to the boundary of the subproblem, right? So that's what this is. So we basically enforce that the dual weight of no point of B goes outside the boundary of the subproblem. And the second condition we add is that all free points of A have a dual weight of 0. So these are the two additional conditions that we introduce. This second condition will look innocuous, but it's very important. Otherwise, we can get trivial solutions. We can essentially set the weight of all points of A to be really large and match all points of B to the boundary. If you don't have this additional condition, we can start getting trivial solutions for the recursive subproblem. So this condition is kind of important in that sense. Okay, let's look at what it means what it means to run this kind of an algorithm in divide and conquer setting. So essentially, you have this problem, and what we'll do is we'll divide it into 4 subproblems, and then we'll recursively find a solution where every point every blue point matches to a red point, or it matches to the boundary of the subproblem. So that's what we end up doing. If you complete this, this is how it will look for the top left subproblem, and we do this for each of the 4 subproblems, right? And then now, once we have solutions from these 4 subproblems, it's easy to merge. All you have to do is collect the matching edges from each of the 4 subproblems and the dual weights from each of the 4 subproblems. When you do this, you get a feasible matching. Like we discussed, none of the blue disks are going to be creating an infeasible edge with a red disk on the other side. Right? They won't be enclosing the red disk on the other side. Okay, so this is this way we can initiate our merge step. Now, what do we do next? Once we have this solution for the 4 subproblems, to merge, all we have to do is erase this common boundary. So between the 4 subproblems, what does it mean to erase? Basically, we end up, so remember, blue points could have matched to this boundary, right? So if you erase this boundary, those blue points now become free again. They end up becoming free again. And all we have to do in the merge step is now run the Hungarian algorithm and compute basically the dual adjustment procedure to match each one of these blue points. Right. So in doing so, we may do one of 2 things. We may find an augmenting part to a red point, or we may find an augmenting part that basically stops us at the boundary. And we end up matching. When we augment, we end up matching the last blue point to the boundary. Right. So this can happen. So that basically is our algorithm. Now, there are several issues when it comes to analysis. If you're not careful, we may not like we may basically get stuck doing all the work at the root. For instance, imagine if your subproblem looked like this, right? You may have a situation where the blue points are close to the boundary, and the red point, which basically when blue point only end up matching to the boundary instead of matching to the red points. Even though you can imagine here that the matching edges are not very long, you may still end up with a situation where all the blue points match to the boundary. So when you erase, you're essentially left with all 3 points. And so you're basically running the Hungarian algorithm from scratch. So you get stuck sort of running this expensive merge step, which takes n cube time or n squared time in this case, right? So a nice trick to overcome that is to sort of use a random shift. So basically what one can do is take this root square that contains all the points, double the side length, and then do some sort of a shift that is random, meaning you move this larger square to the left and below by random numbers between 0 and 1. And when you do that and use that as the initial problem, then what happens is when you recursively shift, your boundaries of the subproblem start to become they are basically selected randomly. And so you can argue that the expected number of blue points that are close to the boundary is small. And that sort of helps us argue that not too many blue points, at least in the stochastic setting, not too many blue points will match to the boundary. Of course, if all of your matching edges were long, for instance, right, like in this example, if all your blue points and red points kind of separated geometrically, they're far apart, then this algorithm is hopeless, right? Basically, if you divide it, all your blue points end up being in one of the subproblems and your red points end up being in the other subproblem, and blue points end up matching to the boundary, and all the work is done at the root. Right? So this algorithm that we saw just now is really meaningful only if your matching edges tend to have small cost, right? If the edge costs become long, then they're not that useful. Okay. So what I'm going to do is, so at least for the stochastic setting, we could sort of prove that basically prove that the running time is n to the 7/4 log delta. And the way the analysis is really simple. What we did is basically argued. So think of this white. Assume that this subproblem side length is 1 for now, and think of this white region, the width of the white region to be about n to the -1/4, right? So what we could argue is that the number of blue points in expectation in this white region will not be more than n to the 3/4. So now imagine all of these n to the 3/4 blue points are matching to the boundary. So that's case one. And second, the blue points that are well inside, they may or may not, if they match to the boundary, the cost of that will be at least n to the width of this white region, which is n to the -1. So what we can argue is that we can show that the matchings we maintain will never exceed a cost of square root of n. So therefore, you cannot have more than n to the 3/4 of these blue points that are in the gray region match to the boundary, because if you do that, then you start to exceed square root of n. Right, so only n to the 3/4 from here can match to the boundary, and there are only in expectation n to the 3/4 many points in this white region. So a total of only n to the 3/4 will match to the boundary. And so when you actually erase this boundary, the amount of work you have to do is n to the 3/4 many searches, these dual adjustments and augmentations. And so each one of which can be done in order of n time, basically n polylog n. And so that leads to this running time of n to the 7/4 log delta. Log delta comes from the fact that, you basically, when you construct this recursion, the height of the recursion tree will be log delta, right? Okay, now back to the original problem we were trying to solve. So essentially, we can, use the same algorithm that I described just now to solve the fixed time vehicle routing problem. The only challenge comes in the following. So imagine you have an instance of the fixed time vehicle routing problem. So this big square contains that, and k is a potentially large number. Now suppose you have a smaller subproblem inside of this, right? Which contains theta of n points. But if you look at the optimal solution here, basically it contains only two, all these theta of n points are covered by two paths, right? Just two paths. So what happens in this case is all the edges, the matching edges will turn out to be really, so if you look at the matching instance corresponding to the fixed time vehicle routing problem, all these edges will be long, right? And so intuitively, if you do a divide and conquer on this, you may end up sort of breaking the optimal edges. And then perhaps one of the risks we run into is that we may have to do a very expensive conquer step at this subproblem. So the question is, can we, like, how do we analyze this? Can we avoid, or how can we overcome this challenge? And so the answer is very simple, actually. It's not like, you can basically argue. So think of this, the subproblem you saw here. Think of doing the following. Think of sort of the side length of that subproblem to be 1. Now do the following. Break, basically create n to the 0.4 many rows and columns, and look at all the points that are in each one of these, right? And then connect the points that are in here in chronological order. So what happens is you end up getting about n to the 0.8 many paths in this fashion. And essentially, if you look at it in the context of matchings, you get a matching of size n minus n to the 0.8 in this graph. So basically, you have matched most of the points in this matching that I constructed, except a small number n to the 0.8 many. And if you look at the cost of these edges, it's not a lot. Each of these edges is about n to the minus 0.4 in length, right? So they're actually pretty small. So all we did here is we showed that there's a very high cardinality, low cost matching that's hidden in each subproblem through this construct. It doesn't matter how the subproblem looks. You can always use this strategy to argue that there is a very low cost. When I say low cost, I mean the average cost of an edge in this matching is going to be, growing. It is about n to the minus 0.4, so it's actually very small. So what we essentially showed is that the number of free points here is at about n to the 0.8. So we have a really large cardinality matching where the average cost of the edge is very small. And that's all we need for the proof. We don't need the actual optimal matching to have a small cost. We need a large cardinality, low cost matching that is hidden in the underlying instance. And so using that, we were able to basically argue that the number of points that match, if we apply the divide and conquer strategy for fixed time vehicle routing problem, the number of points that match to the boundary is going to be small. And and that leads us to this running time of n to the 1.8 log 10. Okay, so let me conclude. Let's see. I'm going to conclude with some interesting open questions. So the first obvious open question is, how much can we push this? Right? We have sub-quadratic time. Can we do better? Can we perhaps get into the 1.5 for the stochastic setting, or even for the fixed time vehicle routing problem? I have a feeling it's hard to beat into the 1.5 because you run into some packing type arguments, which I'm not sure is easy to overcome. At least I don't know how to do it. So into the 1.5 may be feasible. Doing better than into the 1.5 may require some interesting techniques that are not yet, that may actually shed light into the general matching problem itself. Then the second very interesting open question is this. So basically, when I gave the reduction between fixed time vehicle routing problem and online metric match, and the matching problem, what that also establishes is an interesting connection between the offline k-server and the matching problem, right? So now one may ask the same question about online matching and online k-server. Because if you go back to the online problem, basically a reduction implies that the online k-server reduces to a version of the online metric matching. And what's interesting is these two problems have had very different algorithms. There's a different set of algorithms for online metric matching and different set of algorithms for online k-server problem. And so one interesting question is, can we take for instance, the online metric matching algorithms and apply it to design new online algorithms for the k-server. So this is a very interesting direction to pursue. We could ask questions like, what if I have a capacity on the number of edges on each path? Basically, that restricts the number of requests a server can serve. Many of these restrictions immediately make the problem NP complete. So the question is, can we design interesting approximation schemes, for that guarantee that give us 1 plus epsilon approximation, right? Or what if we say that, oh, a request can be served in a fixed time window, which is very short, right? And assume that we have finite velocity vehicle, then can we start designing interesting approximation algorithm for this version of the problem? Intuitively, the reason why this problem is easy is because you don't have the same hardness that you have in TSP, which is you don't have to look at all permutations. You are given the ordering in advance. Like, for instance, if you had just one server, it has to serve request R1 followed by R2 followed by R3. So there's no need to check these permutations, right? But the challenge it's only interesting when you have larger values. Okay, but if you are dealing with short time windows, the same benefit continues to hold. You don't have to really start looking at like the permutations you have to look at are local. They don't have to be global, especially if you have a finite velocity vehicle. So it could lead to interesting set of questions and interesting techniques and both practically useful solutions as well. The one last thing I want to say is that I have an interest on the application side of things for this problem. So I actually got, if you take the New York taxi data, that's about 300,000 requests per day and about 150 million requests per year. So it has about 30,000 taxis. So we can model, so the data that New York taxi gives is the timestamp at which a request was picked up and dropped off. So you can actually reduce the problem of finding the optimal routes for the taxis for historical data to basically solving an instance of fixed time vehicle routing problem. And there are these nice GPU-based solutions we have designed that run in a highly parallel fashion and basically give you really high quality solutions in very small amount of time. For instance, in this example, we could solve instances that are as big as 300,000 in about 70 seconds using a GPU, which is pretty impressive. And so that basically leads us to, gives us the ability to compute these kinds of optimal routes for the large amount of data that exists for New York taxi. And the hope is that one could use that kind of optimal routes and potentially build ML models that could help ride-hailing systems, right? So that's kind of the application side of things. And so there's an interesting, that's an interesting aspect of this problem. Okay, so I'm going to conclude here. So basically, I introduced a new variant of the vehicle routing problem called the fixed time vehicle routing problem, and showed that it is actually equivalent to geometric bipartite matching problem, and then presented a sub-quadratic algorithm for instances where you had bounded spread. The algorithm is simple, implementable, and could be used for identifying cheap routes for taxis to serve requests in New York taxi. Questions?